Good morning. I am Nick Ralston, and today I'm going to be talking with you about selenium and its role in the unified theory of toxicity. Soft electrophiles in particular, but potentially in relation to certain other toxics. We're always looking for answers as scientists, but just like everyone else, we're prone to falling for simple but wrong answers rather than looking deeper and realizing that it takes a slightly more complicated understanding of an issue in order to come up with the proper answers. I'm going to be talking about selenium physiology, and I realize most everyone at this conference is very familiar with this, so I'm only going to spend a brief moment introducing it for the sake of those that may not be familiar with it. But the selenium of the amino acid selenocysteine is the most powerful intracellular nucleophile in the body. And selenoenzymes, which use selenocysteine to perform their essential functions, they're expressed in tissue-specific distributions in all cells of all vertebrates. And among their most important functions is the prevention and reversal of oxidative damage, but they do perform many other functions. And these functions are very important in brain and heart and any other tissues that have high metabolic activity rates. They can't survive without selenoenzymes. The chalcogens, which may be a new term to some of you, they're the group 16 of the periodic table, which includes oxygen, sulfur, and selenium. And the chalcophiles are the elements that like to bond with the chalcogens. And this includes mercury, thallium, lead, cadmium, and a host of other elements. And these elements, when they enter the body, will initially bind with the thiol of cysteine, because sulfur is a nucleophile, and it will enjoy binding and forming a partnership with electrophiles such as the chalcophiles that I just mentioned. But because they're so abundant, those molecular adducts will form first. And that's a good thing in a way because it does serve to buffer the amount that will get to cysteine, but actually has a adverse effect because cysteine molecules are among the many substrates of selenoenzymes, and therefore a soft electrophile that's bound to cysteine will be brought into a selenoenzyme's active site with the electrophile presented directly to the selenocysteine. And because the selenium has a higher binding affinity for those elements than the sulfur of cysteine, it will transfer from the cysteine to the selenocysteine. So in reality, those thiomolecules that initially bind to electrophiles are suicide substrates, and they form and direct the soft electrophiles into the selenoenzyme active sites. So in reality, they may buffer, but they're a buffer that come with a big problem. The toxicity of soft electrophiles is due to their irreversible inhibition of selenoenzymes. And thiols that deliver the soft electrophiles into the selenoenzyme active sites, they will irreversibly inhibit those enzymes. But even worse, they'll form a stable adduct between the soft electrophile and selenium that will impair selenium's availability for subsequent cycles of enzyme or selenocysteine synthesis. The chalcogens and the chalcophiles that love them, the chalcogens are highlighted here in group 16, the oxygen family, and you can see oxygen, sulfur, selenium, tellurium, etc. But the highlighted in yellow are the chalcophiles, which like to bind with the chalcogens. And you can see sulfur and selenium themselves are chalcophiles because you will form sulfur-sulfur bonds or sulfur-selenium bonds or selenium-selenium bonds. But the ones that we worry the most about are like the mercury, the thallium, the lead, the cadmium, the toxic heavy elements. So just to get back to nucleophiles and give a little further detail on what they are, nucleophiles are electron-rich functional groups that are able to donate a pair of electrons. So selenium's able to provide electrons. Sulfur can provide electrons. Oxygen, to a lesser extent, can provide electrons to a electrophile, a molecule that needs electrons or prefers to obtain electrons from other molecules. So the reactive potency of nucleophiles will be determined by their redox potential. Oxygen has less reactivity than sulfur, far less, and selenium has less, selenium has more than sulfur. So the high exposures to soft electrophiles will irreversibly inhibit selenoenzymes and impair its availability. So you can see the binding, the dissociation constants of oxygen, 10 to the minus 27th. That of sulfur is 10 to the 39th, and that of mercury with selenium is 10 to the 45th. So there's a millionfold higher binding affinity between mercury and selenium than between mercury and sulfur. So the interactivity, this thermodynamic difference is responsible for the selenium coming away with the electrophiles. The nucleophilic chalcogen series is serine, cysteine, and selenocysteine with oxygen, sulfur, or selenium in the functional group. But the pKa's are what really matter. Oxygen, the serine of oxygen hardly has much chance at all of being exchanged. In fact, it takes an enzyme to accomplish that. Cysteine has a bit better chance at physiological pH, but still the vast majority of it will be protonated and therefore less reactive. But selenocysteine, you can see drawn with a unprotonated selenium, is because at physiological pH, that's what you'll have. It will be highly reactive with an electrophile. So, as I mentioned, the chalcophiles are the chalcogen-loving elements, such as mercury, thallium, and lead. But you see in this list, I've added a couple of others. I've added gold and platinum. And this is because platinum in cisplatin appears likely to be a very good selenium binder. And arothioglucose, this one we actually know is an excellent selenium binder because it is a specific inhibitor, a highly specific inhibitor of thioredoxin reductase. And it completely abolishes thioredoxin reductase activities by the gold interacting with the selenium. So all we're really talking about here is the hard, soft, acid, base concept of binding predictions. And this is just a general prediction. It's not nearly as good as the quantum modeling, but it provides a fairly good level of understanding. And the methyl mercury form that binds to cysteine, that's a molecular mimic of methionine, which expedites its transport across placental and blood-brain barriers. The plasma membrane is more than happy to bring a methionine across and have it transfer into the intracellular space. So the combination of enhanced toxicokinetics of an element and its toxicodynamics, how it will interact and form the actual functional group that impairs the activity of the enzymes, those together make methylmercury a very potent inhibitor of brain selenoenzymes. Others are likely to be less potent, but still potentially able to impair selenium availability and contribute to the toxicity of any and all other soft electrophiles. Now, there's also a possibility that organics will be competing for binding with selenium. And the alpha beta unsaturated electrophiles, many of these are notable neurotoxic agents. And so organic soft electrophiles will have weaker selenium binding, but mass action effects, their overall abundance can sometimes be higher. And so if they're 10 times less affinity, but 10 times more abundant, they might even out to be a similarly toxic material. And of course, we're not talking about tenfold, we're actually talking several log orders of differences in their binding affinity compared to like the metallic soft electrophiles. But we may be talking several orders of magnitude higher availability of these molecules too. So concurrent exposures to these, even if they only take a little, several that take a little may end up causing greater vulnerability to other soft electrophiles. Now, one of the things that has to be considered is some of these molecules, even if they are good soft electrophiles, steric hindrance may disable them or may impair their availability for transfer into the active site of a selenoenzyme. So several things will need to be considered as organic soft electrophiles are evaluated. But there are many that are notable toxic, neurotoxic agents. Acrylamide, the aflatoxin has a very notable toxicity, not necessarily only considering neurotoxic, but between neurotoxic effects and other disease-causing effects of these agents, I think it's important to consider their possible selenoenzyme inhibition consequences and their ability to impair selenium availability. These are the xenobiotics, the ones that can be acquired from exposure to environmental sources, but there are also endogenous sources that are numerous and may be even more abundant since they are constantly being formed. And there's also several of these that are notable as far as potential risks or problematic molecules that need to be considered. So I'm just proposing these for your consideration. I'm not proposing these as immediate as the metals. The metals we know are toxic. Several of them we know are very toxic soft electrophiles. But among these, notice the one in the lower right-hand corner, the acetyl alpha D galactosamine. That one actually doesn't look like it would be that great of a selenium binder, but this one actually forms the selenose sugar that a good amount of the selenium exits the body bound with. So there are pathways in which even a molecule like that can bind selenium and potentially become a less available form. So, in summary, as the most potent intracellular nucleophile, selenocysteine is the molecular target of soft electrophiles. Soft electrophile bindings with selenium will be inversely related to the soft electrophile toxicity levels. If it's a very high binding affinity, it'll take less of it to sequester selenium and cause toxic effects. And the toxic effects of high soft electrophile exposures will be in relation to the selenium status of the exposed individuals. Low selenium individuals will be far more vulnerable to soft electrophiles than high selenium individuals. And for instance, if we're talking pharmaceuticals, the therapeutic effects probably should be gauged in relation to the selenium status of the individual. If its effects are through the soft electrophile binding actions, you need to know the selenium status of the individual prior to determining the pharmacological dose for that individual. So to sum everything up, hindsight is 20/20. Figuring stuff out takes a bit. Foresight is 50/50. We can only guess. Sometimes we have only the most moderate of guesses. So foresight is 50/50. But insight, which is what I'm suggesting, those of you that are listening to this will have to be the ones that will find out the actual answers to these questions that I'm posing. And insight is going to be timeless. I look forward to hearing your questions and look forward to seeing the results of your future research. So thank you very much for all of your efforts, and I appreciate having had the chance to share this with you. I intend to be present for Zoom for questions.